So consider the square loop that is given in the problem and in here, and we know that we're moving through 0, 0 to L0 to LL to 0L and then back to 0, 0. And because there's a dependence on the x value for the forces, you notice that F4, if the x value for the entire length is 0. So since this is true, then F4 is 0 for the entire length, which means it doesn't contribute any work. And if you notice the so leg 1 and leg 3, the force is perpendicular to DL, which implies the work is 0 as well because of the dot product, right? So the work total is going to equal work from leg 1 plus work from leg 2 plus work from leg 3 plus work from leg 4, but all of them except for leg 2 are going to be 0. And note that leg 2, the x value is L, so that means that our force is going to be C times L J hat. So the work then total is going to equal the integral from L0 to LL of this F dotted with DL, which is going to be the integral from L0 to LL of CL J hat dotted with DL J hat, or the integral from L0 to LL of CL DL dy. Right? In this case, DL is in the dy case. And so the work total we can rewrite then is the integral. Since we're only looking at the y values, this would be from 0 to L of CL dy, which is the same as CL integral from 0 to L of dy, or CL times y from 0 to L, which gives us C times L times L minus 0, or CL squared. Right? And yes, well, why is this work total important? And the reason is the following. If work total for our closed loop is 0, it implies a conservative force. If the work total for closed loop does not equal 0, it implies a non-conservative force. And since C does not equal 0 and L does not equal 0, it implies work total is not equal to 0, which implies a non-conservative. Force is what we have, or it's not represented by a potential energy. Same thing.